of log of d of x. It is p data of x log of d of x plus what is the expectation of 1 minus log of d of g of z? It is p of z log of 1 minus d of g of z dz. Now, my goal is to, so this is d of x, this is integration with respect to z. Now I want to make to do an integration with respect to just one variable. So a simple change of variable, we can say that z is just g minus 1 of x, and dz is just g minus 1 derivative with respect to x d of x. So here, so it is equal to integration of p data of x log of d of x. So it is d of x, so I don't change it. But the next term, as I said, I want to make everything integration of everything with respect to x only. And that's why log of 1 minus d of x, g minus prime of x d of x. And g minus prime multiplying by pz g minus 1, I call this pg of x, p of generator. It's like implicit probability of generator. So this is equal to, so the first term is just the same thing, plus the second term is now pg of x, because we have defined pg of x, log of 1 minus d of x. And then you notice that we want to maximize this with respect to d. P data of x log of d of x plus pg of x log of 1 minus d of x. So let's maximize this with respect to d. So we want to maximize this with respect to d. And what do we do when we want to maximize with respect to d? We just take derivative with respect to d. From elementary calculus, we do this p data of x log of d of x plus pg of x log of 1 minus d of x. Derivative with respect to d and then set it to 0. The first one, if you take derivative with respect to d, it becomes pg of x, and log goes to the denominator, if you remember from elementary calculus. And this term, if you take derivative with respect to d, you may notice that p data divided by d of x. And I said set the derivative equal to 0, and what we obtain is d of x is equal to pd plus bg, what I claimed before. So we proved what I claimed before. Now we want to say that C of your generator is the maximum with respect to D of generator and D, and this is equal to P data of X log of P data of X divided by P data plus PG of X plus pg of x log of pg divided by p data plus pg. You don't mind if I divide it by 2 here and then divide it by 2 here, and the overall things divide by log 4. So nothing has changed. And you will notice that this is just a KL divergence. So if you work on this at home, you may notice that this is just the KL divergence of P data and P data of x plus P generator of x divided by 2 plus KL divergence between P generator of x, P data of x plus P generator of x divided by 2 minus that log 4 that we created. And you notice, you know that KL divergence is positive. So if you work on this, you may notice that PD is PD plus PG over 2, and PG is equal to PD plus PG over 2. If you want to maximize this should happen. Because this term and this term should be equal to get minimized. Same for this. That's why we have two conditions. And if you simplify this, it means that P of data is equal to P of generator. It means that at the beginning, P of data, it cannot capture P of G. For example, P of D is this and P of G is this. But after a while, after several epochs of your PyTorch algorithm, you may notice that, oh, they are coming. So it is fooling the discriminator. The generator has fooled the discriminator because at the end of the algorithm, they are almost the same. It means that their distribution of data and distribution of generator are the same implicitly. Look, we are doing this implicitly. There is no probability in our neural networks. We are doing it implicitly. And that's thing that many people don't understand. Many students do not understand. And now I want to talk about infoGAN. infoGAN is just you add a controllable term. It's just a GAN plus an information neural networks. I mean, a neural networks for the information part, which I call it Q. So in 2016, they created an article which maximizes mutual information between a subset of latent variables and the observations. For example, a disentangled representation, for example, Z1 could be facial expression, Z2 could be eye color. You could be anything. I mean, Z3 could be absence of eyeglass. Z4 could be identity of a person. Z5, for example, aging, anything you imagine. And the GAN is, so I explained it, and now I want to add something new, some disentangled representation. I want to control. I don't want to say that it creates one. I want to say it creates, for example, a one that is a little bit unusual, but is rotated. They are the same thing. And for example, we wish the model automatically chose to allocate a discrete random variable to represent the digit from 0 to 9. So this is one, and the other variable is just the thickness. Your digit could have some thickness. So another variable could represent that. So we decompose the input noise to Z, which is the source of incompressible noise. But we have a C as well. This is the latent code that will target salient structure, semantic features of the data distribution that I told you. P of C1, this latent code, C2 and CL, so we have L latent codes, is I from 1 to L, P of C of I. So this is exactly like GAN, but we add another term, which is mutual information. So we minimize with respect to generator as usual. We maximize with respect to discriminator as usual, but V of I stands for information. V of I of D and G is equal to V of D of G. This is the same thing as GANs, but now we add an extra term, which is called minus lambda I of C and G of Z and C. But you should know the loss of this. So the loss of this extra term is the, first of all, category loss between predicted and ground truth. So predicted category and ground truth category. So loss is this plus the continuum loss. We have a category loss, we have a continuum loss. So the continuous loss is predicted code, again, predicted code and ground truth code. And you know this I that I told you, I of between the code and, for example, I say the code is, the thickness is big. The generator of Z and C, it should have mutual information with that. It means that how much is reduced from the uncertainty, H of C minus H of C condition on G of Z and C. And this is equal to expectation of X if you draw it from generator of Z and C, of expectation of, now your code is just drawing from a distribution C condition on X, and then log of P of C prime X plus H of C. So this is equal to expectation of X, G of Z and C, of the KL divergence between P and Q. Remember that KL divergence is positive, and then plus expectation of C prime drawn from P of C conditioned on X of log of Q of C prime conditioned on X. Because this term is greater than equal to 0, so this term is greater than equal to expectation of X, G of Z and C, expectation of C prime, C condition X, log of Q of C prime condition on X, plus H of C. So the architecture is like this. We have noise. We have, for example, one continuous code. The other one is discrete code. And we give all of them to our generator. Our generator creates fake images, fake MNIST data. So it's a fake image. But the fake image goes to the discriminator. So discriminator says that, oh, it's real or fake. If your MNIST digit is real or fake. But now in infoGAN is the generalized GAN, so we add another neural networks, Q. And it produces C1 and C2. And these are Q of C prime condition of X, because X is before discriminator, it's generating the image. And C1 is, so this is discrete. It is one hot encoded. For example, we have 10 classes in MNIST data. For example, 2 could be 1, 0, 0. And so this is the one hot encoding of that. And we also have this continuous variable, which is between -1 and 1. So you can say the degree of rotation of digits. But don't worry, Q could be just a softmax. It could be a normal softmax or linear layer on top of discriminator. So let's say it's just a normal softmax. But you can think about it, it's just a linear layer of discriminator. So there is no much more complexity. I mean, there's no function class in there that you need to worry about. So I explained infoGAN. So this is called infoGAN. But if you implement this in PyTorch, you may notice, oh, it still people cannot do it in very few iterations and small epochs, and because you need to change lots of parameters. I mean, everything is a problem. So it's a framework. First of all, how do you deal with this G? It could have several convolutional layers. I mean, what is the architecture of that? In discriminator, what is the architecture of that? For example, first you map it, there are several convolutional layers, and finally you have fully connected layers, and then finally you give it to a just 0 and 1. So I mean, you give it to a discriminator to see if it is fake or real. So all of these things are open problems. I mean, you have several hyperparameters to choose. So all of these define the architecture. The architecture depends on this, depends on the generator, depends on even this Q, this little Q. Of course, that doesn't matter because it's very small. But the architecture depends on how you generated what is the noise. Of course, it's a Gaussian, but the real parameters are the parameters of the architecture of the generator and discriminator, and so you see that the difficulties of deep learning. And I will create another playlist. It is called Deep Learning in 2000